Hello and welcome to AST121's tutorial on Kepler's laws. In this video, I'll first go over very briefly the discovery of Kepler's laws. I'll then state the three laws. I'll then go over Newton's generalization of Kepler's laws and show a simple derivation of Kepler's third law for circular orbits. Lastly, I'll go over some applications and work problems. Johannes Kepler discovered his three laws in the early 17th century, with his third law being published 10 years after the first two. Kepler's laws were revolutionary for their time. Not only did they support Copernicus's heliocentric model of the solar system, which was controversial back then, but they also stated that the planets' orbits were elliptical rather than perfectly circular. About a century later, Isaac Newton proved that Kepler's laws could be generalized to any system of two bodies that orbit one another. And Voltaire was the first to call Kepler's laws laws in the 19th century. So what are Kepler's laws? Kepler's first law states that the orbit of a planet forms an ellipse with the sun at one focus, as shown in this diagram here. For bookkeeping purposes, I'll denote the semi-major, or long axis of the ellipse, as A, and the semi-minor, or short axis, as B. Kepler's second law states that the sun-planet radius vector sweeps out equal areas in equal times. Now what does that mean? Let's go back to this diagram. We have a planet orbiting the sun, and the sun-planet radius vector is just the line connecting the sun to the planet. As the planet moves from point A to point B, the sun-planet radius vector sweeps out this area here, shown in blue. A little bit later in its orbit, the planet moves from point C to point D, and during this time, the planet-sun radius vector sweeps out an area shown here in pink. Now, if these two areas are equal to each other, then Kepler's second law states that it takes the same amount of time for the planet to go from point A to point B as it does to go from point C to point D. But the distance between point C and point D is much longer than the distance between point A and point B, which means that the planet must be traveling faster as it's closer to the sun than when it's further away. Kepler's third law states that the square of the period of revolution of a planet is proportional to the cube of the semi-major axis of its elliptical orbit. In other words, p squared is proportional to a cubed. Kepler found that the constant of proportionality in this equation is the same for all the planets orbiting the sun. Now, if we were to use units of years for the period and AU for the semi-major axis, we can get this equation here. P squared in years is equal to a cubed in AU. Now, this is obviously true for our own Earth by definition, because the Earth takes 1 year to travel around the sun, and the radius of the Earth's orbit around the sun is 1 astronomical unit by definition. And because the constant of proportionality is the same for all the other planets, and indeed all the other objects orbiting the sun, they can all follow this equation. Now, this can only be used for objects orbiting the sun. Using it for any other purpose will give incorrect answers. Kepler determined his laws from planets moving around the sun, and he did it observationally. Newton, on the other hand, used his laws of motion and the universal law of gravitation, shown here as equation 3, to generalize Kepler's laws. It turns out that the three laws we just covered, elliptical orbits, equal areas in equal times, and period squared proportional to semi-major axis cubed, hold for any body of mass little m orbiting a much more massive body with mass big M. Little m could, for example, be a satellite, and big M the Earth. Now note that little m orbiting big M isn't entirely accurate. Both little m and big M actually orbit the center of mass of the two-body system. When little m is much smaller than big M, the center of mass is inside object big M, just because it's much more massive. And so we can say that little m orbits big M. In fact, Newton showed that a slightly more complicated version of Kepler's laws also works for the case where little m and big M are comparable to each other. That's beyond the scope of this video, though. Newton's derivation, which is also beyond the scope of this video, also leads to the general form of Kepler's third law, shown here as equation 4, where A is the semi-major axis of the object's orbit, which we defined a couple of slides earlier. Note how both little m and big M are included in the equation. In the situations that we consider in this class, little m is always a lot smaller than big M, so big M plus little m is approximately equal to big M, and we can just drop little m out of equation 4 altogether. We can derive Kepler's third law for the limited case of a circular orbit, where A is equal to r, the radius of the circle. Take an object of mass little m, orbiting a much more massive object of mass big M in a circle. This is a uniform circular motion, So we need a centripetal force to keep little m in its orbit. And the centripetal force necessary is given by this expression here. Now, in this situation, the centripetal force is provided by the force of gravity. So we equate the centripetal force to the force of gravity. We then do a little bit of algebra, and out comes equation 5, which looks nearly identical to equation 4, Kepler's third law above, except that we only have big M in the denominator rather than big M plus little m. And this is because we've assumed that little m orbits big M, which requires that little m be much smaller than big M. And as a result, little m actually drops out of the expression here. As I noted earlier, a variant of Kepler's laws still works when little m and big M are about equal to each other. Where Kepler's laws break down is when you no longer have two objects in your system. Say you have a planet orbiting a binary star system. A couple have been discovered in recent years. In this situation, the planet's orbit is quite a bit more complicated and might actually be unstable. Now, our own solar system has multiple planets and numerous smaller bodies, and so it's not just a two-body system. But because the gravitational pull of the Sun is so much stronger than the pull of any other body in the solar system, we can effectively treat a planet or any other small object and Sun as a two-body system rather than a many-body system. Lastly, let's go through a few examples of how to use Kepler's laws. So here's a simple one. Uranus and Neptune have periods of 84 and 165 years. How far are they from the Sun? Well, this is the solar system, so we can simply use p squared in years is equal to a cubed in astronomical units. Or, rearranging this a little bit, a in astronomical units is equal to p in years to the 2/3. For Uranus, 84 to the 2/3 is equal to 19.2, and for Neptune, 165 to the 2/3 is equal to 30. So Uranus is 19.2 astronomical units away from the Sun, and Neptune is 30 astronomical units. Now let's do something a little bit more complicated. Orbiting Jupiter, which is about 5.2 astronomical units from the Sun, are the Galilean moons Io, Europa, Ganymede, and Callisto. They're named after Galileo, who discovered them. Telescope observations of Callisto from Earth show that Callisto orbits Jupiter once every 16.7 days in a nearly circular orbit, and its maximum angular separation from Jupiter is 498 arcseconds. What is the mass of Jupiter? Now we know from Kepler's third law that if we knew the semi-major axis of Callisto's orbit and its period, we could figure out the mass of Jupiter. The question above gave us the semi-major axis of the orbit in arcseconds, so first we need to convert that into a physical length. And we can do that using the small angle formula, which is theta, the angular length of Callisto's semi-major axis, is equal to L, the physical length, divided by d, the distance between Earth and Jupiter. Now first we convert 498 arcseconds into radians. So 498 arcseconds divided by 3,600 arcseconds in 1 degree is equal to 0.138 degrees. 0.138 degrees times pi over 180 radians in 1 degree is equal to 0.00242 radians. We take the Earth-Jupiter distance to be the same as the Sun-Jupiter distance, which is 7.78 times 10 to the 11 meters. That isn't entirely accurate because, depending on the geometry of the solar system, the Earth can either be closer to Jupiter than the Sun or further away from Jupiter. And so we'll just ballpark it and say it's about the same as the Sun-Jupiter distance. Plugging in all of our values into the small angle formula, we find Callisto's orbital radius to be 1.88 times 10 to the 9 meters. We can then rearrange the general form of Kepler's third law, equation 4, a couple of slides back, to obtain the mass. The mass of Jupiter plus the mass of Callisto is equal to 4 pi squared a cubed over g p squared. If we plug in those numbers, we get that mj plus mc is equal to 1.89 times 10 to the 27 kilograms. Now remember that the mass of Callisto is much less than the mass of Jupiter, so we can safely say that the mass of Jupiter alone is 1.89 times 10 to the 27 kilograms, or about 317 Earth masses. In conclusion, planets orbiting the Sun, or more generally, objects orbiting bodies much more massive than themselves, trace out an ellipse with the Sun, or massive body, at one focus. The planet Sun, or object massive body, vector sweeps out equal areas in equal times. And p squared is equal to 4 pi squared a cubed over g times the sum of the masses. And for our own solar system, p squared in years is equal to a cubed in astronomical units. Lastly, here's some further reading for those interested in learning a bit more about Kepler's laws and Newton's law of universal gravitation. If you go to the uploaded PDF of this lecture on Portal, you'll be able to click the first two links. Thanks for watching, everyone.